Hello my scholars, this is my school channel and my name is Abiola. For this video lesson we are going to be tackling the JAMB CBT past question for the subject Physics, the year 2009. Do not go anywhere, stay with us because we'll be right back. Welcome back to my school YouTube channel. For this video lesson, we are going to solve questions 34 to 49. So join me as we start with question 34. Which of the following can conduct electricity owing to the presence of free mobile electrons? Okay, so basically the emphasis should be on the presence of free mobile electrons only. Okay, let me just attach that only to it to be more specific. Okay, so that should be copper because we know that metals conduct electricity, okay, due to the presence of free mobile electrons, metals like copper. All right, so when it comes to germanium and silicon, these are very good semiconductors. The carriers of electricity in them include electrons and holes. Holes, they are the positive one, electrons are the negative one. So depending on the type of conductor you're talking about, either the N type or the P type of semiconductor. All right, so we come to grapefruits. Of course, we know that grapefruit conduct electricity, and that is based on the electrolyte that is present there, that's citric acid. So the correct option for this question is option D for copper. 35. When a pentavalent impurity is added to a pure semiconductor, it becomes what? So let's key into the word pentavalent. So when you say pent, that is 5. Valence, that is 5 valency, right? So when you talk about pentavalent impurities, examples include antimony, arsenic, and the likes. Okay, so when you use antimony or arsenic, okay, as impurity or dopant, okay, so when it is added, either you are okay. Let's go back to the question. When a pentavalent impurity is added to a pure semiconductor, what you get is an N-type semiconductor. All right. So, but when you use trivalent impurities or dopants, okay, like your boron, your indium, what you should get is a P-type semiconductor. So pentavalent, what you are going to get, or what you should get, is an N-type semiconductor. Insulators, they are just materials that do not readily do not allow the flow of electric current through them readily, like they oppose the flow of electricity, okay, readily. So take note of the word readily. Okay, so we have an intrinsic semiconductor. We are talking about semiconductors that are still in their pure state, all right, the high type of semiconductor. You've not added any impurity to them. Okay, so the correct option once again is option B, an N-type semiconductor. 36. The value of x, y, and z respectively in the expression m raised to the power x, l raised to the power y, t raised to the power z for the universal constant g are what? So we can just use these simple techniques, okay, to carry out. So recall that we're going to use this, right? gm1 m2 over r squared, right? So this is the constant that we are asked to find the dimension. So once we do this, then we have fr squared equals g m1 m2. So dividing both sides by m1 m2, right? m1 m2. So I can write this as g, right, equals fr squared over m1 m2, right? So the dimension for force is ml t raised to the power minus 2, right, times this is distance, that is 2 lengths, that is l raised to the power 2, isn't it, over for mass, that is m, isn't it? So I have m, then another mass, I have m. Okay, so this is gone. So basically I have to bring this up, That means I have m raised to power minus 1, isn't it? We have L times L raised to power 2. That should be L raised to power 3, right? Times T raised to power minus 2. So if we want to properly assign the letters to their values, okay, so we should do this. This is X, right? This is Y, and this is Z. So that should be minus 1, 3, minus 2. Minus 1, 3, minus 2. Minus 1, 3, minus 2. Option B. So option B is the valid option. 37. An aircraft attempts to fly due north at 100 km per hour. If the wind blows against it from east to west, okay, so at 60 km per hour, its resultant velocity is what? Okay, so if we try to scope out diagram for this, okay, no, this is due north. Remember your cardinal points. So we have 600 kilometers per hour, right? Then we are told the wind, right, blows against it from east to west. So this is towards our west, of course. Okay, so at what speed? We have 60 kilometers. Okay, we can see that. All right, some we intend putting it here, but I prefer to work with it. So we're asked to find our resultant velocity, isn't it? This is what we are looking for. So you can decide to probably join your diagram like this. Okay, just pardon me. Okay, so you see what we have right here now. So we have 100, rather, this is 100, not 600. So I have 100 here, I have 60 right here. So if you look at this, this looks like a right angle triangle that's just standing on this side. Okay, so if we try to sit it down, you can see from here, isn't it? So you see what we have very well. So that means this side you are looking at is the same thing we are looking at here. So I can just put it this way so that we can use our Pythagoras theorem. All right, so remember we said hypotenuse square, right, equals opposite square plus adjacent square. All right, so that should give me 60 square, right, plus 100 square. You can say 100 square plus 60 square, isn't it? Okay, so I should have my 60 square, that is 60, that is 3600, right, plus 100 square, that should give me 10,000. So if I have this up, my hypotenuse square should be 13,000, right, 600. So the square root of 13,600 is roughly 117, roughly. Let's just bring it to that, 13,600 kilometer per hour. So you can see that this actually makes sense. Why? You can see the hypotenuse side is always the longest side. So you can see here is 100, here is 60, or you can see here is 60, and here is 117. So that is what we are looking for. So we don't just stop here. Remember that we are told that we should find the resultant velocity. So you can see it's between the north and the west. Okay, so how do we do that? Very easy. So you can use your tan theta, right, equals opposite, okay, over adjacent. So that should give us my 60 over 100. So that's 0.6. So tan inverse of 0.6, right? 0.2, you know, theta equals the tan inverse. If I bring this out, so that is roughly 30.9 something. So I can just bring it to 31 degrees. So 31 degrees, that is actually dealing with north and west. So let's go back to the screen to pin that down. Okay, so we have 117 kilometers per hour, and it's between north and west. Okay, so that's the dealing. So that is where we have option C. So option C is very correct. 38. A car accelerates uniformly from rest at 4 meters per second square, right? So how far will it travel in the fifth complete second? So we can use S equals UT plus half AT squared, right? Remember this equation of motion. Of course, there are other methods that you can apply, but I would just like to stick to this. Okay, so from rest, that means 0 times t. So basically this is gone out of the equation. So what I should have left is half, right, times A times T squared. So in 5 seconds, right, we talk about the 50 seconds, but now in 5 seconds altogether, that should be half, right, times A, acceleration, okay, that's 4, times 5 seconds, that is 5 raised to power 2. This is 2 here 1, 2 here 2. So 5 raised to power 2 is 25. 25 times 2, that is 50 meters. So in 5 seconds, it's going to travel 50 meters. What about in 4 seconds? So that should be half times 4 for acceleration times the time in 4 seconds, right? So 2 here 1, 2. So I have 4 raised to power 2, that is 16. 16 times 2, that is 32 meters. So in 4 seconds, it traveled 32 meters. All right. So we are not told that how far has it traveled, right, in the 5th complete second. So that is from the 4th second to the 5th second. What is the distance? So you just minus this. So 50 minus 32, that should give me 18 meters. So it's completed 18 meters in the 5th complete second. So let's go back to the screen to pull out 18. Yeah, option D. So option D is very correct. Why not try out our Myschool tool? So you just need to do is to click on the link in the description below. It's going to get you to the Myschool website. Right there you get to download the Myschool mobile app for your Android devices, or you can check our Myschool software for your laptops and your computers. So join me as I solve question 39. A body of mass 12 kg, 12 kilogram, to put that way, traveling at 4.2 meters per second, collides with a second body of mass 18 kilograms, 18 kg at rest. So this is 0. Calculate their common velocity if the two bodies coalesce after collision. Okay, so that means they stick together. That's what that word means, they stick together. Okay, so we're just going to use this. So since they stick together, they are going to have a common velocity. So instead of writing out this, right, so their velocity is common. So I will just have it this way instead. V into brackets M1 plus M2. Okay, so M1 we're given 12. Okay, the speed at which it was traveling was at 4.2, right? 4.2, okay, plus the mass M2, that is 18 kg, right? From rest, that is 0, okay, equals the common velocity which we are looking for, then the addition of both masses. Okay, so I have this times this should give me 50.4, right? This is 0. 18 times 0, that is 0, plus this is still this, so I have equals 12 plus 18, that is 30V. So if I divide both sides by 30, of course you can punch your calculator, but I'll just decide to do it this way, which is V equals 50.4 over 30, right? So that is roughly 1.68, yeah, 1.68. If I want to, I can say maybe 1.7 meter per second, velocity. So I used speed earlier, but the question is talking about velocity, so we are still good. So we have velocity, all right. 1.7 or 1.68, where do we have that? We have that in option D. So option D is super correct. Please do not forget that you need to motivate us continually. All you just need to do is to hit the like button. Also click on the subscribe button and always tap on bell notification for you to get informed immediately we upload the next video content. Question 40. The terminal velocity of a ball bearing falling through a viscous fluid is reached when the ball ceases to accelerate but moves with a uniform velocity. So you can call that constant velocity, or you can call it terminal speed, your terminal velocity, still the same, right? So, at this point, the viscous force is proportional to the terminal velocity. And you should take note of this, when it comes to this experiment or this setup, there are 3 forces that we should note, okay, that we should take note of, okay? So we should be talking about the upthrust, we talk about weight and viscous force. So the correct option to this question is option D. At that point, the velocity is uniform. 41. The pressure of 2 moles of an ideal gas at a temperature of 27 degrees Celsius and volume 10 raised to power minus 2 meter cube is what? We are given the molar gas constant as 8.318. So we just use this equation. We'll use this. PV equals nRT, number of moles, right? So the question requires that we find the pressure. So I will just say my P equals nRT over the V, right? So if we're going to fix in the values, right? So number of moles, that is 2, right? Times the molar gas constant we're given here, that is 8.313 times the temperature, right? It's given in Celsius, but we are going to convert to Kelvin scale. So that is 27 plus 273. That should give us 300, right? Then divided by the volume, which is 10 raised to power minus 2. Okay, so this is what I know. 2 times 8.313 times 3. I know it's 300, okay? Or I can refer to this as 10 raised to power 2. Okay, so that I can work with standard form. Okay, so all this put together, this, and this should give me 49.878. Yes, 49.878. Okay, so we have times 10 raised to power 2. Okay, then we still have this here, 10 raised to power minus 2. So we have 10, we have 10. Then that will be minus, bracket, minus 2. Okay, so that should be 49.878 times minus, that is plus. So 2 plus 2, that is 4. So basically, I can still work around this. If I want to shift my decimal point, I can say 4.9878 times 10 raised to power 5. Okay, so you may not go through this long procedure. Okay, you can just punch your calculator from here, then you should get something like this. All right, so we have 4.9878 times 10 raised to power 5, converting it to standard form. So let's go back to the screen and see if we have that. Okay, so we have 4.9878. So if I want to bring that together, compress it, that should give me maybe 4.99 thereabouts. Okay, yeah, 4.99 times 10 raised to power 5. Yeah, 4.99 times 10 raised to power 5. So option A is the correct option. 42. The wave phenomenon demonstrated in the diagram above is what? Okay, so that is diffraction, you know, the ability of wave to bend around obstacles or corners, okay, just to have its expression. Okay, so generally I would just say the properties of waves, okay, they include reflection, refraction, diffraction, polarization, and interference. Okay, that's just additional information. So the correct option is option C. The phenomenon we are seeing here is diffraction. So option C is super correct. 43. The diagram above represents the graph of the force F applied in stretching a spiral ring against the corresponding extension X. Okay, so the force constant of the spring is what? All right, so just according to Hooke's law, right? So we have this force is directly proportional, right, to the extension or the compression produced. Okay, so we have this. So this is the force constant. Okay, this is the constant of proportionality. You can call it the force constant, the elastic constant, or the stiffness of the material. So this is what we are looking for, right? So we should have K equals F over E. Once we divide both sides by the extension E. Oh, it is referred to as X in the question. So you see the same thing. So either I use E or X, we are good, please. Okay, so we have our K. So just at any point at all, okay, so on the F, you notice that there is 40, then the next to it is 2. So that will just be 40 divided by 2. Or you try using the next one, which is 80 against 4. That is 80 divided by 4. Or you use 120 against 6, right? So that is 120 over 6. So which of the values, okay, you decide to use, you should still get the same answer. All right, so I have 40 divided by 2, that is 20. 80 divided by 4, that is still 20. 120 divided by 6, that is still 20. So we can see this. So our answer. So let me just say I use 40. Okay, that is against 2. 20. Remember the unit, Newton per meter, or you can write it this way. Newton meter raised to power minus 1. So we are looking for 20. Let's go back to the screen. Okay. So very well, we have that. Okay, yeah, option A. So option A is very correct. 44. If a light wave has a wavelength of 500 nanometers, okay, in Hertz, what is the frequency of the wave? So we are given the speed as 3 times 10 raised to power 8. All right, so that should be V equals F lambda, right? Okay, so we are looking for frequency, so that will be F equals V over lambda, right? Okay, so what is our V? Okay, we are given 3 times 10 raised to power 8, right? We have over our lambda, which is the wavelength, over 500 nanometer, that is 500 times 10 raised to power minus 9. Okay, so I can just say this to this, right? I can say 3 over 5, right, times 10 raised to power 8. This is also 10, isn't it? So this is 500. If I want to convert 500 to standard form, so I can say this like this. I can say 500 is actually equals to 5 times 10 raised to power 2, isn't it? So I have 5 times 10 raised to power 2 times 10 raised to power minus 9, isn't it? So I have times 10 raised to power 2, which is minus, of course, everything is going to affect everything here. Okay, or I can just work it. Let me just work it from the denominator so that to not be mixed up. Okay, then times 10 raised to power minus 9. So I have 10, right? I have 10. So 2 minus 9, that is minus 7. Okay, so I'm going to bring this up. So that will be times 10 raised to power minus, this divide actually stands for minus, then this minus 7. So I have 3 divided by 5, that's actually 0.6. Okay, you can save yourself a lot of stress. Just punch your calculator. All right. Okay, times 10 raised to power minus times minus, that is plus. So 8 plus 7, that is 15. Okay, so that's 10 raised to power 15. Or if I want to bring this to proper, okay, so a proper form, I can just say 6. I can bring this back to 6 by just lending 1 from here. So that should give me 6.0, right, times 10 raised to power 14. So this is what I should have for my frequency has. Okay, so let's go. 6.0 times 10 raised to power 14 has Hz. Okay, so we have 6.0 times 10 raised to power 14. If we left the value, okay, in 0.6 times 10 raised to power 15, but we are bringing into this because of the options we are given. So option B is the right option. 45. Calculate the EMF of the cell in the above circuit if its internal resistance is negligible. So this arrangement is in parallel. Okay, then we have the current. All right, so we can use the formula. Okay, first let's find our resistance. Okay, so since in parallel, this is what we should have: 1 over R1 plus 1 over R2. So 1 over R equals the arrangement. We have 3 ohms and 6 ohms. So I have 1 over 3 plus 1 over 6. Okay, so if I work around this, my LCM should be 6. 3 is 6, that is 2 times 1, I have 2, plus 6 and 6, that is 1, times 1, I have 1, so that is 3 over 6, 3 here 1, 3 here 2, so basically I have 1 over 2. So that is 1 over R equals 1 over 2. By the time I cross multiply, 2 comes here, so that means my R equals 2 ohms. So at this point, we can use this if we like, or we can just say V equals IR. You know, at the point where the resistance is 0, you can say that the EMF, of course, is equal to the terminal voltage. But let me just work with this. Okay, I into bracket R plus R. Okay, so I should have my EMF equals, the current supplied is actually 4 amperes, right, into bracket my R plus R. So the resistance here is actually 2. We are told negligible, so I can take that as 0. So 2 plus 0, that is 2. So I have into bracket 2. So that is E equals 4 times 2, that is 8 volts. So let's sort out 8 volts. Okay, we have that in option B. So option B has what we are looking for. Asking questions on the Myschool website is simply easy. All you just need to do is to click on the link in the description below. This is going to take you to the Myschool website. Right there you get to ask your questions and our solution providers get to help you out. All right, so let's move to question 46. From the diagram above, if the potential difference across the resistor, capacitor and inductor are 80 volts, 110 volts, 40 volts respectively. All right, so the effective potential difference is what? Or I can say the effective voltage is what? So this is the formula that we are going to use. So we have this is our effective voltage, right? So we have V square R. You can see this is the symbol for resistance, inductor, capacitor. All right, so for our resistance, what do we have? We have the resistor is the first one. Okay, that is 80 volt. That is 80 raised to power 2. Right. Then we have this. Then for our inductor, yeah, that is 40. Right. Okay, for our inductor that is 40. Very well. Minus our capacitor that is 110 volts. Okay, so basically I have 80 squared, so that is 64,000, right? Plus into bracket 40 minus 110, that is 70, minus 70, please. Okay, so I should have 6,400. All right, so this is minus 70 raised to power 2 actually. That is minus 70 times minus 70. Minus times minus, that is plus. 7 times 7, that is 49. Then I have 2 zeros. So I have added to 4900. So if I add this up, this is 6 plus 4, that is 10. 4 plus 9, that is 13. So I should have my V square equals 11,300. Yeah, 11,300. So I have to find the square root of both sides to eliminate this square. So I mean V equals the square root of this. So roughly that is 106.30 whatever, yeah. So this should be my answer, 106.3. Yes, I think I can bring it to that. So let's see if we have that. Yeah, scanning through the options. Okay, that's option D. So option D is the correct option. Please note that your contributions and reviews are very important. Okay, so all you just need to do is to kindly use the comment section below. Please indicate the question number and the explanations you'd like to share. 47. A progressive wave is represented by y equals 10 sine. We have 100 pi t minus your pi x, okay, over 34. Okay, so two layers of the waves. They are separated by 153 centimeter and they have a phase difference of what? Okay, so this is the standard formula when it comes to progressive wave. Okay, so if you compare it with what we are given there, you realize that the part with minus pi x over 34 actually represents the phase, right? So this is what we are going to do. Standard, we know that this equals kx. Or you can say this is actually the same thing as saying 2 pi, right, over this. So remember we have our x here. So we can see it. So that means we are going to compare this with what we are given in the question. So in the question we are given the phase angle as pi x over 34. Over 34. So what can we do if we cross multiply, right? So we are looking for this, the wavelength. So I will have 34 times 2, that is 68. So I have 68 pi x, right, equals the wavelength, which is lambda, then the pi, right, then the x. So dividing both sides by pi x. Okay. So I can see that my wavelength is actually 68. All right, so that's 68. So we are asked to find the phase difference. Okay, so recall from this that this is actually 2 pi x over this, right? So that will be 2 times the pi. Okay, the horizontal displacement there. Okay, we can say 2 layers separated by 153 centimeter. That's times 153 over 68. So if we divide this using our calculator, we should have 4.5 rad. Remember, we measured this in radians. Okay, so if you want to convert this to degrees, this should give you 810 degrees. All right, but I feel that is too fast. So either you say 90 degrees or 810 degrees, it should still give you 1. So it's either 810 or 90. So which of the two that is supplied in the question? Because if you punch your calculator sign 810 or sign 90, you still get 1. So let's go back to the screen and see if we have either 810 or 90. So we have that in option C. So option C is the right option. Number 48. Which of the diagrams above shows the position at which a small ball bearing is in neutral equilibrium? Okay, so we have various positions here. Okay, we want to talk about the types of equilibrium. We have the stable, we have the unstable, then we have the neutral. So where do we point to neutral equilibrium? You know, a body is said to be in neutral equilibrium if, when it is slightly displaced, all right, it comes to rest in its new position. It tends to come to rest in its new position. So such examples should include when a cylinder or a cone, an egg is resting on its side. Okay, you can imagine that that picture or those pictures. Okay, or you talk about a ball, a sphere, okay, resting on an horizontal smooth surface, and that is what we have in option D. So option D is in neutral equilibrium. So the correct option here is option D for letter D. 49. The process of energy production in the sun, in the stars, okay, that process is nuclear fusion. Okay, that's option B. Nuclear fission, you can see that in uranium-235, okay, when it splits into smaller nuclei like your krypton and your barium. Okay, so the correct option is option B. Nuclear fusion is actually what we see, okay, when it comes to the energy, the enormous production of energy, okay, in the sun, in the stars. Of course, the sun is a star as well. So option B is the correct option. We've come to the end of this video lesson, but there is still more to come. All you just need to do is to hit the like button. Also, click on the subscribe button and always tap on that bell notification for you to get alerts immediately we upload the next video content just for you.